Welcome to this Junior Cycle Higher Level Maths revision video. This video is going to focus on trigonometry. As part of that, we're going to look at Pythagoras Theorem, trigonometric ratios to find missing sides, trigonometric ratios to find missing angles, working with multiple triangles, and finally some real-life examples. So for this video, we're going to look at specifically right-angled triangles, and this is a section from page 18 of your formula and tables book. So as you work through the video, it will be a really good idea for you to have your log tables open on page 18. Two sets of formulas that are important here are our sine, cos and tan trigonometric ratios, and then there is also Pythagoras' theorem. Often students find it easier to learn sine, cos and tan off, which is absolutely fine, and then they often use this for Pythagoras. But Pythagoras theorem, the formula for this is quite straightforward, and many students also know that off by heart. If it is a bit rusty, or if you can't remember what they are, please use page 18. So let's just do a really quick revision on right angle triangles. So I have a right angle triangle here. A right angle triangle is one that contains a right angle. Do be aware that it's important that you never assume that it's a right angle triangle. There is always something to indicate, like our square here, to tell us that that is a right angle. Right angle measures 90 degrees, and a really important word that you need to know is the word hypotenuse. So a hypotenuse is the longest side of a right angle triangle. Now sometimes that can be difficult to spot if there's very little difference between the sides and if the triangle itself has been rotated. So another way to remember where the hypotenuse is, it's across from the right angle. So the side that is across from the right angle is always the hypotenuse. So Pythagoras' theorem, what he discovered was in a right angle triangle, the square of the hypotenuse is equal to the sum of the square of the other two sides. So let's take a look at this. Here's my hypotenuse here, my longest side. Here's my right angle. What he discovered was this length of this side is 5, and if I drew a square, which is 5 by 5, it would have an area of 25. The other two sides have a length of 3 and 4 respectively. This then has an area of 9, the square on the side of 3, and the square on the side of 4 is 16. And what he discovered was that 25, the big square, is equal to the two smaller squares added together. So this can be simplified into our formula and used, but sometimes it's important for students to see this visually to really understand what he was talking about. So this picture here, hopefully you can see drawing your squares on each side. So if we want to simplify this, we can use the formula which is on page 18, and it's c squared is equal to a squared plus b squared, where c is equal to the hypotenuse. It doesn't matter which arm you label A and which arm you label B, the important one is C. So once you get C correct, the other two do not matter. So now let's use Pythagoras' theorem to help us to work with some questions. Use the diagram on the right to calculate a value for x. Give your answer in third form. So that's important. That's working with our square roots. So first thing I'm going to do, I label my triangle CAB. I then write down my formula, which is c squared equals a squared plus b squared, which is x squared is equal to 3 squared plus 3 squared. X squared is equal to 9 plus 9. X squared is equal to 18. X is equal to the square root of 18. So x, when that is simplified down, although square root of 18 is in third form, it's not in the simplest third form. So we can simplify that even more, and we get 3 root 2. If they asked us to convert that or to give the answer to so many decimal places, that would easily be done from our calculators. The second example, find the length of the short side in a right angle triangle. So here we're looking for the value of y. Again, give your answer in third form. So again, first thing I do is I label CAB. I write down my formula. C squared is equal to A squared plus B squared. C is 3 squared is equal to y squared plus 1 squared. 9 is equal to y plus 1. Sorry, y squared plus 1. So what we want to do is we want to subtract 1 from both sides. So 8 is equal to y squared. So just flipping that to make it easier. Y squared is equal to 8. Y is equal to the square root of 8. So in this case, we get y is equal to 2 root 2. So again, it's important you don't leave your answer in the third form you get, but that you simplify it as much as you can. So now let's talk about Pythagoras' theorem and also the converse of Pythagoras' theorem. So Pythagoras' theorem is one that sits between both trigonometry and geometry. So because it sits in both, we can look at it from more of a trigonometric point of view. So working with Pythagoras before working with our sine, cos and tan, or our trigonometric ratios. Or we can look at it from a more geometry point of view. So we might be using Pythagoras' theorem and then work with our other theorems we have from geometry, such as all the angles add up to 180, etc. So here we have the theorem of Pythagoras, which basically tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. This is specifically when we have a right angle triangle. The converse of this theorem says if the square of one side of a triangle is the sum of the square of the other twos, then the angle opposite the first side is a right angle. So basically, if we don't know that the triangle is a right angle triangle, we can use the Pythagoras theorem to prove that it is a right angle triangle. And we know then whatever side is the longest must then be the hypotenuse. So this leads us to something called Pythagorean triples. So this is a term that does tend to come up, and we've seen it at both junior cert and leaving cert. And basically the term Pythagorean triple means three numbers such that put into the formula they satisfy c squared equals a squared plus b squared. So the example here is 3, 4 and 5. They form a Pythagorean triple because 5 squared is equal to 3 squared plus 4 squared. And remember, the hypotenuse when we're talking about a right angle is always the longest side. So this will always be the square of the longest side, or in this case the biggest number, will equal to the sum of the squares of the other two numbers. So there are infinitely many Pythagorean triples, but here are some examples. Often as students work with trigonometry, they start to notice these Pythagorean triples, and they start to notice that when you have 3 and 4 and you're missing the hypotenuse, hypotenuse will always be 5. So they start to see these patterns emerge. So we have 3, 4, 5, 5, 12, 13, 7, 24, 25, and so on. So now let's take a look at a question which involves Pythagorean triples. Given any two positive integers, m and n being greater than m, it is possible to form three numbers, a, b and c, where a is equal to n squared minus m squared, b is equal to 2nm, and c is equal to n squared plus m squared. These three numbers, a, b and c, are then known as a Pythagorean triple. So the first thing they ask us to do is for the values m equals 3 and n equals 5, calculate a, b and c. So a is equal to n squared minus m squared. So that gives me 5 squared minus 3 squared, which is 25 minus 9, which is 16. So a is equal to 16. B is equal to 2nm, which is 2 times n, which is 5, m, which is 3. And that is 2 times 5, which is 10, times 3, which is 30. And c is equal to n squared plus m squared. So c is equal to 5 squared plus 3 squared. So c is equal to 25 plus 9. So C is equal to 34. So if the values of A, B, and C for part I are lengths of the side of a triangle, show that the triangle is a right angle triangle. So what we want to say is if C squared is equal to A squared plus B squared, if that is true, then it is a right angle triangle. So let's work with that. So we have 34 squared is equal to 16 squared plus 30 squared. So 34 squared is 1156. 16 squared is equal to 256 plus 30 squared is 900. So 256 plus 900, we get 1156 equals 1156. Therefore, A, B, and C are the lengths of the sides of a right angle triangle. And it's important to note then that the hypotenuse would be the longest side, so that was our 34. And this is how we would work with the converse of Pythagoras. So we're still using Pythagoras, but instead of knowing its right angle, we're saying, well, if Pythagoras' theorem, or that formula we have for Pythagoras' theorem, if that works, then this must be a right angle triangle. So now they say, if n minus m squared, 2nm, and m squared plus m squared are the lengths of a side of a triangle, show that the triangle is right angled. So at this point a lot of students would ask, but we've just done that in the previous part. So what we've done in the previous part is we've proved that it's true specifically for two values. One value for when m is equal to I think our m was equal to 3 and n was equal to 5. So that's all we've proved it for. They're asking us now to prove this so that it's true for any values of n and m. So by subbing in, we only prove it's true for one value. If they want us to prove it true in general, we cannot sub in. And this is more an algebra piece than anything. So we have a is equal to n squared minus m squared. We have b is equal to 2nm, and we have c, which was equal to n squared plus m squared. And we want to basically again prove that c squared is equal to a squared plus b squared. So we have n squared plus m squared, all to be squared. A squared is n squared minus m squared, again all to be squared, plus 2nm, all to be squared. So I'm actually going to work these all separately. I'm going to leave a bit of space to come back. But I'm going to do n squared plus m squared squared is n squared plus m squared times n squared plus m squared. Separate out our brackets, n squared bracket n squared plus m squared. Plus m squared bracket n squared plus m squared. Multiply that out. N to the power of 4 plus n squared m squared plus n squared m squared plus m to the power of 4. Cleaning that up, we get n to the power of 4 plus 2n squared m squared plus m to the power of 4. So that's kind of our first little piece here. Our second piece, we have something similar. We're going to work that through. So we have n squared minus m squared squared, which is n squared minus m squared times n squared minus m squared. First thing I'm going to do is split our brackets. N squared bracket n squared minus m squared times n squared minus m squared. We get n to the power of 4 minus n squared m squared minus n squared m squared plus m to the power of 4. Simplifies down to n to the power of 4 minus 2n squared m squared plus m to the power of 4. last piece is going to be this piece here. And this is 2nm all squared. So if you can remember your rules of indices, everything needs to be squared. We get n squared m squared, which ends up giving me 4n squared m squared. So let's work through this and put this back. So what we got for the answer for part 1 was n to the power of 4 plus 2n squared m squared plus m to the power of 4 is equal to, part 2 we got n to the power of 4 minus 2n squared m squared plus m squared, and the last part was plus 4n squared m squared. Now on the right hand side we have two like terms that we can add together to clean it up. Other than that, everything stays the same. 2n squared m squared plus m to the power of 4 equals n to the power of 4. So we have minus 2n squared m squared plus 4n squared m squared. So we get plus 2n squared m squared. And sorry, that should be m to the power of 4 plus m to the power of 4. And what you see is the left hand side is equal to the right hand side. Therefore, this is a right angle triangle. So although very algebra heavy, it is working with Pythagoras' theorem. So we see Pythagoras very much on paper 1 popping up in the form of algebra, as well as on paper 2 in maybe a more practical term. So it's one that they like to put into different places. So just to be aware of the idea of Pythagorean triples, like in this question where they actually use that term, and be aware of the idea of using the converse of the theorem of Pythagoras so that we can prove that a triangle is a right angle triangle. So now let's look at labeling a right angle triangle. So we've labeled it for Pythagoras. So when we were dealing with Pythagoras, we still talked about this being the hypotenuse. Well, what if I instead said, well, let's talk about the labeling of a triangle with respect to an angle. And our angle here is A. So suddenly which side is which becomes a lot more important. So when we dealt with Pythagoras, we said the hypotenuse, yes, that was really important, we identified that correctly, but the other two, it didn't really matter. Now the other two sides, it really does matter because we're talking about this angle here. So our other two sides are labelled as opposite, meaning opposite the angle, and the second is the adjacent, and adjacent is another word for beside. It's not a term we use a lot in English anymore, but it is an English term for beside. So it is the side beside the angle. So my advice, and the way that most students prefer to work, is first of all label your hypotenuse, then label the side which is opposite, and then adjacent is the final side left, or it's the one beside it. That tends to be the one that students find most difficult to remember. So we have 3 trigonometric ratios that we needed at junior cert higher level, and they are the sine ratio. So sometimes mispronounced sin because it's S-I-N, but that's just short for sine, S-I-N-E. So the sine ratio here, and the sine of A is given as the opposite over hypotenuse. So there are two sides there. So in this triangle, our opposite side, bear in mind, is always opposite our angle. So then we have the cosine ratio, or what's known as cos. So cos of A is equal to the adjacent over the hypotenuse. So in this case, we're talking about the angle is beside the side. So that side that's beside the angle, so adjacent. And the last one is our tangent ratio, or simply known as tan. Tan of A is equal to opposite over adjacent. Okay, so again, remember, I'm constantly looking, the angle is opposite. Okay, so notice that in each of those ratios, because we have 3 sides, there is one side missing. So the sine ratio does not use adjacent. The cosine does not use opposite, and tan does not use hypotenuse. And that's important to remember because one of the big questions students have is, how do I know which one I should use? And in most cases, only one will be
will be able to be used because of the information we have. If you have all three sides, then you can use any one you want and it won't make a difference. So one way that students remember this is using SOHCAHTOA. Now, one of the drawbacks of using SOHCAHTOA is, do you know how to spell it? So if you use SOHCAHTOA, first of all, make sure you know how to spell it. So SOHCAHTOA. And that is a way for us to remember that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. Sometimes people make up little rhymes to go with the letters. So one is silly old Harry caught a herring trawling off America. There's lots of different versions that I've heard. Remember that these are also available in your log tables. Now, when we're working with our log tables, they can be a little bit tricky because they don't call the sides opposite, adjacent, and hypotenuse, which often exam questions want you to label your sides as that. So although we do have these formula and you could work with your log tables, it is not the best idea to do so. So now let's use some trigonometric ratios to find the missing sides. So the diagram on the right shows a right angle triangle with hypotenuse of length 10. So that's all given in the picture. And use trigonometry to find the length of the side marked X and give your answer in third form. So the first thing I'm going to do is I'm going to label. So this is always my hypotenuse, and because this is across from or opposite the angle, this is my opposite side. The other side is my adjacent, but I'm not going to label that because it's not relevant. I don't want it and I don't know anything about it. So the next thing I'm going to do is I'm going to write down what will help me. I'm going to use SOHCAHTOA, and I want to figure out, well, which one's right. Well, I don't have adjacent, so straight away I'm saying, well, I can't use tan and I can't use cos. They both have an adjacent, an A in them. So I'm going to have to use sine. So I say my sine of A is equal to opposite over hypotenuse. So I'm always writing down my formula first. Now, the only thing I didn't label on my diagram was my angle, so I'm going to put that in now as A, and I'm going to write down sine of 60 degrees is equal to X over 10. So that's my substitution. At this point, you have two options. You can work out sine of 60 and leave it in third form, or if you want to wait, we can do that in a second. So what I would actually work through to make sure it was as accurate as possible is I would actually get rid of my fraction first. So to get rid of my fraction, I multiply across by the common denominator, which in this case is 10. This cancels, and what I end up with is 10 times sine of 60 is equal to X. So you can put that straight into the calculator, or you can instead go straight to sine of 60. So again, bear in mind that they want this in third form. When this comes out of your calculator in third form, it's root 3 over 2, and that equals X. And our final answer then, when we simplify that, is 5 root 3. So the calculator will do all that. You could have subbed in for sine of 60 before you multiplied across by 10. However, if you're working to decimal places, if you have to start rounding, or if you don't get a nice third answer, it can be difficult to work with decimals. So I would tend to get in the habit of doing any multiplication that you want to do first, and then to do your substitution as late as possible. So now let's look at another question. In the right angle triangle shown in the diagram, one of the acute angles is 4 times as large as the other acute angle. Find the measures of the two acute angles in the triangle. So we're going to talk about something that we would have covered in geometry, and specifically one of our theorems. So one of our little theorems told us that it was possible to figure out which angle was the biggest, which angle was the smallest, and therefore which angle was kind of the middle angle of a triangle. So the rule is always this: the biggest angle is always opposite the biggest side, and that is true in this case because this is my 90-degree angle. It is clearly the biggest, and it's across from my hypotenuse, which is the longest side. Looking next, okay, then the next biggest side is this one here. Let me just get my highlighter. So it's this one here. So the next biggest angle is this one here. The smallest side is this side here, and therefore this is my smallest angle here. So is that hugely important? Well, I suppose if you want your diagram to be correct and to look correct, then you might really want to do this. It's not a huge, it won't impact hugely on this particular question, but it's a good place to revise. So they told us that one acute angle is 4 times as large as the other. So if this was x, we'd say that this was 4x. Now maybe by looking at it you would say, oh, well, straight away I knew that that was the bigger angle, and that's absolutely perfect as well. So now I have 3 angles in the triangle in terms of x, but I can use my theorem which states that all the angles in a triangle shall add up to 180. You can simplify that more and say, well, if all the angles add up to 180, and I know that there is a 90-degree angle here, therefore the other 2 angles should add up to just 90. So whichever way you want to work that is absolutely fine. So that should be 90. So I have 5x equals 90. So x is equal to 90 divided by 5, which is equal to 18 degrees. Now, be careful, measure the 2 acute angles. So this one we've just worked out is 18 degrees, but remember that the other one is 4 times that, so the other is 72 degrees. Okay, so then the other one is going to be 4 times 18, and that gives us 72. And what I do at this point is I double check. 72 plus 18, does that give me 90? Yes, plus 90 will give me 180. So the next part is the triangle in part I is placed on a coordinate diagram. The base is parallel to the x-axis, and find the slope of the line L that contains the hypotenuse of the triangle. Give your answer correct to 3 decimal places. Okay, so they've not given us a huge amount of information, except I do know that this is 18 degrees and this is 72 degrees. And they want me to find the slope. And if you think back to our coordinate geometry, slope can be calculated using rise over run. I won't be able to use the formula from my log tables here because I haven't been given any points. But using rise over run is not going to work here because we have no lengths. So I don't know what length this rise is, and I don't know what length this run is. However, you might start to notice something here. If I was to sketch out a right angle triangle, which we have, and I label this as my angle, labeling for trigonometry, this will be the hypotenuse, this will be my opposite because it's opposite the angle, and this is my adjacent. Now, how we label it for coordinate geometry and for slope is this will be my rise, and this is my run. So if I do rise over run, in trigonometry terms, that is opposite over adjacent. And if we think back to our trigonometric ratios of SOHCAHTOA, TOA, we are talking about opposite over adjacent, we're talking about tan. So we make a very interesting connection here. The slope is equal to the tan of an angle. So when they asked us for the slope, what we actually are being asked to do in this question is simply to find tan of 18 degrees correct to 3 decimal places. But without making that connection between slope and tan, that question is near impossible. So it's really important that you see that connection here and that you remember it. Okay, so let's use a trigonometric ratio to find the angle. So in this question, they've told us that the triangle ABC is given such that the length of AB is equal to 2. So I'm going to put that on my diagram. The length of BC is 1. So one really good trick when you're doing any kind of question, especially if you've been given a diagram, is to read any piece of information they give you and check, is it on my diagram? The majority of cases it will be there. However, if not, fill it in, because the more you can see visually, the easier the question will be. So find the length of AC correct, or giving your answer in third form. So we're looking for this, and because we're looking for it, I'll call it X. So I'm dealing with two sides and I want to find the third. So actually what I'm dealing with now is Pythagoras. So this is C. I'm going to label this A, and I'm going to label this B. So using Pythagoras, C squared is equal to A squared plus B squared. I sub in. We get 2 squared is equal to x squared plus 1 squared. So 4 is equal to x squared plus 1. Subtract a 1 from both sides and we get x squared is equal to 3. And the last step is to say x is equal to the square root of 3. And our answer here is straight away in third form as requested. So now what I'm going to do, I'm going to cross off this x and I'm going to say, well, actually now that's root 3. So now it wants us to write the cos of BAC. So let's identify the angle BAC. Okay, so you start at B, you come down to A, and you go across to C. So the middle letter is always telling us what angle specifically we're talking about. So we want the cos of, I'm going to say angle A. Now to help us do this, we're going to have to write down SOHCAHTOA. So let's see, SOHCAHTOA. We're looking at this one. So actually cos is equal to adjacent over hypotenuse. So let's go back to our triangle and label it. This side here is my hypotenuse. This side here is my opposite the angle, and this is my adjacent. I had already labeled this triangle for Pythagoras, and just so it didn't get confusing, I've just changed my colors. So now I can say the cos of A is equal to adjacent, which is root 3 over the hypotenuse, which is 2. So that is the first part. Write cos of BAC. Done. And now they want us to find that angle. So what we're going to do here is basically I want to find the angle A. And I can't put the cos of A into a calculator because I can't put letters into my calculator. So I basically want to find A on its own, knowing that cos of A is root 3 over 2. So what we use in this case are called inverses. So we use A will be equal to what's called cos inverse of root 3 over 2. So cos inverse, that little -1 means inverse, appears on your calculator above sine, cos and tan. So above sine you get sine inverse. Above cos you get cos inverse. Above tan you get tan inverse. And to get those, if you're using a Casio, you press your shift button and then either sine, cos or tan. In this case we're going to use cos. So we're going to put that into our calculators and the answer we get is 30 degrees. So we get A is equal to 30 degrees. So if we want to use our trigonometric ratios to find an angle, we instead use our inverse. Okay, so what way you can think about this is we basically have brought it across to the other side and it is using the inverse of that function, okay, or the opposite of that function to find the angle. So it's important that you practice those and it's important that you know how to get your angles given knowing the value of any of the trigonometric ratios. Now let's look at an example that involves multiple triangles. So the diagram below shows two right angle triangles which are ABC and ACD. And on the diagram I'm looking at both triangles and I notice that yes, the right angles have been indicated. They have right angles in B and D respectively. The length of AB is 10, the length of AC is 12, AD and DC are both equal to x as shown, and the angle BAC is marked Y. So the good news is everything that they've told us is given on the diagram. It doesn't need us to add anything. Use trigonometry to find the angle Y and give your answer correct to 1 decimal place. So we're looking at Y, so we're going to focus on one right angle triangle. So we're going to focus on the triangle ABC. So what I find extremely useful to do in cases like this, i.e. where you have multiple triangles, is to sketch it out again relabel it A, B, C, 10, 12, and this is my y in here. I then come along and I'm going to label. So I have an angle, so this is my opposite, which I don't need. This is my adjacent, and this is my hypotenuse. So we're looking at something that has the adjacent and hypotenuse. So we're looking at, let's write down our SOHCAHTOA, or whatever you use to figure out your trigonometric ratios. We have adjacent and hypotenuse, so we're dealing with cos. So we have the cos of A is equal to adjacent over hypotenuse. Filling in what we know, we have the cos of y is equal to 10 over 12. If we want to work out y, we want to use what's called cos inverse to work out the angle itself. So cos inverse of 10 over 12, I haven't even simplified that down, but you'll get the exact same answer if you do. 33.557, and they want that correct to one decimal place, so just this one, and we look what's next, and we get 33.6 degrees. So now it asks us to find the value of x and give your answer correct to two decimal places. So now what we're going to focus on is we're actually going to focus on this triangle here. So we're going to focus on the second triangle. And again, I'm going to suggest that you do some kind of sketch to help. So it's good to know that's the right angle. These two sides are both the same. They're both x, and this is 12. Now, often students find it difficult in questions like this because they're saying we don't actually have enough information. But although there are two sides that we don't know, the fact that both of those sides are equal in length mean that we can easily apply Pythagoras' theorem. So we have c here, a here, and b here. C squared is equal to a squared plus b squared, and filling that in, we get 12 squared is equal to x squared plus x squared. So we get 144 is equal to 2x squared. So then dividing both sides by 2, we get x squared equals to 72, and x is equal to the square root of 72. So this question wants us to give that answer correct to two decimal places. So when we do that, we get 8.485, two decimal places, 1, 2, and then we cut. Since we have a 5, we're going to round up, so we get 8.49. There's no units there, so if you want, you can write units. So notice that part I and part II, although they were linked into these two triangles, the way that the question was structured, if you weren't able to get the correct answer in I, it had no impact to the part of part II. So now let's look at a question which takes what we know about trigonometric ratios but challenges us to use it in a different way. So f is an angle in a right angle triangle, and the cos of f is 6 over 11. So the first thing they're talking about is the fact we have a right angle triangle, but they didn't give it to us. So let's sketch out our right angle triangle. And they've said the cos of f, so f must be an angle in the right angle triangle, and we can assume that it's not the right angle triangle. So if we had a triangle like this, we would have it labelled so that this was the opposite side, here was adjacent, and here was my hypotenuse. They've told us that the cos of f equals 6 over 11. So going back to our SOHCAHTOA, or whatever you use to remember your ratios, we know that cos is given as adjacent over hypotenuse. So that means they've actually given us the length of two sides. Now, we know that that might not necessarily give us the correct length, but it will give us the ratios in which the sides compare. So we're able to work on this triangle and say, well, this side is 6 and the hypotenuse is 11. So by drawing a diagram of the right angle triangle, find the value of sine of f. So if we want to work with sine of f, the formula from up here is opposite over hypotenuse. Now the problem is, at this point, I could fill in the hypotenuse is 11, but I don't actually know the opposite. So I'm going to have to work out the opposite side here. The only way to do that is to work with Pythagoras using c squared is equal to a squared plus b squared. So working that through, we get 11 squared equals c squared plus b squared. And we get 121 is equal to 36 plus b squared. So taking 36 from both sides, we get 121 minus 36. And we get b squared is equal to 85. So b is equal to the square root of 85. So this opposite side is the square root of 85. If you put square root of 85 into your calculator to see does it simplify down, you'll see that it won't simplify down any further, and that's as simple as it can be. So now I can come along and I can fill into this sine of f formula that the top or that opposite should be the square root of 85. Again, you can put that into your calculator to see if it can be simplified further, which it can't, so that is our final answer. So quite a straightforward question, but the way that it's being presented to us may prove a challenge because often we forget that we have been given the information when we're given that ratio to be able to draw the triangle and in turn work out another or missing side. So now let's talk about two words that appear as we talk about real-world examples in trigonometry, and that is an angle of elevation or an angle of depression. So the first is, if we're talking about angles of elevation, it's the angle between the horizontal and an object above the observer's line of sight. So what we mean is it's this angle down here. So this is my angle of elevation. Think of the word elevation, it means to go up. Think of an elevator. So as we move from the horizontal upwards, that gives us our angle of elevation. The angle of depression is between the horizontal and the object below the observer's line of sight. So here we're looking downwards. So this angle here is called the angle of depression. Now often in questions when they talk about these, they also show what they're talking about so we don't get confused, but it is important to know these two particular words before we start looking at real world examples. So now let's look at a real world problem, and this is asking us a tree 32 meters high casts a shadow of 63 meters long. Now, as I said before, a really good method to approaching questions is if you're reading through it and you have a diagram, constantly check that each piece of information that you've been given in the type or the text, you've also been given on the diagram. So in this case, the tree of height 32 meters, that has not actually been put on the diagram. So just to make our lives a little bit easier so it's a bit more visual, I'm going to write this in. So there's our 32 meters. The shadow of 63 meters, that is given. Calculate theta, the angle of elevation of the sun, and give your angle in degrees and minutes. Correct to the nearest minute. So just a little quick word on theta, which is an angle. Theta is a Greek letter and it looks like an O with a little line through the middle of it, and this is often used, and we see it more at Leaving Cert than we do at Junior Cert, but it's just often used to represent an angle. Other Greek letters you might see are alpha and beta. This does not change anything about the question, and if you really hated it, you could replace it with the angle A and simply rewrite the theta as you got to the end. So one thing that I find useful when we're dealing with real world problems is to re-sketch this triangle. Again, apologies, it's quite hard to sketch straight lines on the computer, but you would of course, even with the sketch, use a ruler. So we have this little piece like this. I think it's good to re-sketch the triangle because it takes any kind of fussiness away. We no longer see a tree, we no longer see a sun, it doesn't matter, we're not getting confused by any of that, we're back to just having a triangle. So if we were labeling it, here's my hypotenuse, but there's nothing going on with it, so I don't really care about that. We have our adjacent here and we have our opposite. So we're talking about this angle here, which they've labeled theta. So I'm going to write down how I remember my sine, cos and tan, however that is. I'm going to use SOHCAHTOA, and I'm talking about opposite and adjacent. So that must mean I'm dealing with tan. So I have the tan of theta, and that's going to be equal to opposite over adjacent. So my tan of theta in this case is 32 over 63. So to work out the angle, we use what's called the inverse of the trigonometric ratio. In this case, it's going to be tan inverse of 32 over 63, which we can put into our calculator. And that gives us 26.927677785. Now, just be careful, they've asked us to give our answer in degrees and minutes correct to the nearest minute. So what we want to be able to do here is to convert that answer into degree, minute, seconds. So what we're going to use is your degree, minute, seconds button on the calculator. And when you do that conversion, you're going to find that theta is given as 26 degrees, 55 minutes, and 39.64 seconds. Now, we want to correct the nearest minute, but remember there are 60 seconds in a minute. So 39, it's gone over halfway. So this, when we round it, is going to round to 26 degrees, and this 39.64 means our minutes are going to round up to 56 minutes.